He's going to talk about normal forms with negligible small divisors for a class of non-autonomous Hamiltonians. Thank you very much.
Thank you, Alex. First of all, let me thank the organizers for this chance to talk about my work. I want to like to talk about this result on normal forms with negligible small divisors for a quite general class of non-autonomous Hamiltonian systems. That is a joint work with Stephen Wiggins. And let me go straight to the model. We have this classical Hamiltonian, which is time-dependent in an aperiodic way. So that is the novelty, let's say, with respect to the classical setting. And the variable lambda is essentially the autonomous equivalent of the system that you can say below. And the setting is standard. The only thing that I want to remark is that t varies in the semi-axis. That is actually a fundamental assumption. Okay, that is the main reference. This is also the QR code of the link. And the results are taken from there. A bit of history, and I would like to convince you that these problems are very interesting. And everything started with Posterity in 1974, and he considered a non-autonomous version of the classical Siegel problem. The perturbation in this case is a perturbation which is dependent on time, but asymptotically it is independent on time. So this gives already the setting that we will find again later. And then we have this work by Giugili and Zender, and there is a proper Nico-Rorschach type result. That is obtained by considering a system which is in the form of a slowly time-dependent potential. So in the form of kinetic plus potential, but the potential is slowly time-dependent. Actually, it can be seen that this is, and it's also reasonable to expect that this is a fundamental assumption, because otherwise you are able to produce a perturbation which gives resonances with the integral part. So that is actually a fundamental assumption. This result has been generalized in Bonemura and Wiggins and myself. In particular, in the last paper, we gave explicit bounds on the speed of the time dependence. So we give an explicit bound of how this time dependence should be slow. Another question, which is classical along the perturbative tradition, is it possible to establish the persistence of the Diophantine flows along the tradition of the Kolmogorov result? Okay, with an assumption on the time dependence that we will see soon, it is possible to establish the equivalent of the Kolmogorov theorem. Okay, so that is more or less the theoretical, let's say, background. Let's have a look at the application. There's this paper, 1998, by Malott and Wiggins, that emphasizes the importance of these results in the context of Lagrangian transport. So the importance in finding those invariant objects, such as tori, is an obstruction, obviously, to the Lagrangian transport. So it's very important to give a theory that establishes this existence. And I shown recently that there's a peculiar problem in which the setting can be given as a integral system with a periodic time dependence. If you consider, basically you have to consider traveling wave in a semi-infinite channel with a rough bottom. Usually the bottom is supposed to be periodic, But if you take a rough bottom, the top of the traveling wave, and if you look at the streamlines, you have an elliptic point. So the question is, does this elliptic point persist under this perturbation? The answer is yes, because of the result that I'm going to show you. Obviously, we are interested in celestial mechanics, so that is the last of a series of papers by Fresson and et al. And this gives, obviously, the setting is stochastic, but that gives us the idea that not everything in the solar system is periodic or quasi-periodic. Okay, and so when we started to study those kind of systems, we had in mind some. We hope to find some examples in which we were motivated by them, in which you have perturbations which are not quasi-periodic or periodic, such this model that is suggested there. And recently, this other paper by Goliath, Timopoulos, Foucault, and Celletti, in which you have a periodic time dependence due to a time reparametrization. That is another kind of problem. It's true that the solar system have let's say, a quasi-periodic intrinsic nature, but if you introduce a time reparametrization, you lose everything. Okay, so if you think, for example, to the Levi-Civita time reparametrization, it's the same thing. The Levi-Civita changes the time, so you lose the quasi-periodic dependence. Okay, let me start with the setting. The setting is the analytic setting, is the classical analytic setting that uses the Cauchy estimates, so we will need complexification and a suitable set of holomorphic real analytic functions. And then we have to measure these objects, and that is the time-dependent version of the Fourier norm. So this is, we measure functions not with numbers, but with function of time. Okay, why? Because we have this key hypothesis, the time decay. Okay, I agree that it's a quite strong hypothesis. But let me say that we have two remarks to point out. The first remark is that A can be small. So we have no lower bound on A as long as A is greater than 0. So in principle, it can be also a very small, a very slow decay. And the other thing is that the proof can be done in the same way if instead of this exponential decay, you have a summable function. So you can also take a capital L1 function, the proof can be obtained as well. That is a paradigmatic case, let's say. And that is, the result is twofold. Okay, that is the first part. If we suppose that the integrable part is isochronous, we are able to find a convergent normal form that casts the Hamiltonian in this form. We call this strong Birkhoff because the normal form that you obtain is quite different. In the standard Birkhoff case, you have h of I because you need to store all the resonant terms during the normalization process. We have exactly omega I. And then you have to impose in the classical Birkhoff normal form the no resonance condition. But here you do not need this condition, and I will show you why in a short while. And furthermore, you don't have a reminder. That is a convergent normal form. On the other hand, we have this other theorem that gives you less in some sense because you weaken this hypothesis on h of I. That is a classical Neco-Roche, in the flavor of the classical Neco-Roche theorem. Obviously, there are some differences. For example, the remainder is exponentially zero, asymptotically zero, sorry, and as well as the canonical transformation. So, as a consequence, both the systems are perpetually stable. That is a key difference with the classical equivalent of those results. Okay, very nice. And let me give you just a hint, just the proof in a nutshell without addressing all the details. The first theorem, as I said to you, is constructed by finding a generating sequence He, which as you can see is independent on eta. That is a key point. That was a feature already considered in Giorgili-Zen in 1992 and has a clear meaning. You don't want the transformation to change the time because it's not clear what does it mean a transformation that changes the time. Okay, and furthermore you don't need it. And that's why the small divisors are negligible. That is the elementary step of the proof. You take the homological equation, and now you have eta. So that gives rise to a time-dependent term. So the classical homological equation, which would be I lambda equal f, now it's an ordinary differential equation, which is linear and non-homogeneous. This can be solved. Pay attention that now lambda is real. So, is it a problem if lambda is 0? Not if f is summable, because that integral exists for all time. That's the difference. In the standard setting, you don't have summability. You have just a quasi-periodical function that oscillates continuously, so you don't have this. But in this case, you are able to find a proper bound. How? By choosing in a suitable way the coefficients, and then you have this lemma. This lemma gives you the possibility to iterate the scheme. That is the meaning. As you can see, there are some small divisors, but those are the classical small divisors arising from the Cauchy estimates. How do you fight them? By using the quadratic feature of the scheme. That is a very classical property. It's used in all the nationals of scheme. So the concept behind the negligibility of small divisors is that the quantity lambda plays no role in this case. So if you suppose that the function is summable, you have no problem. Just one more minute to give a sketch of the proof of theorem 2. We have used the Lie transform method, which is very well suited to treat normalization problems that are made of a finite number of steps. So we need to find this R key functions. What is the difference with respect to the first case? You remember that the lambda was real. Now it's no longer real because omega, which depends on I, you need to extend. You need to complexify. So you have also a complex part in the formula 5. Okay, so this can produce some unbounded terms because you no longer have oscillation. There is also a real exponential term. How do you overcome this problem? You give up at each step a bit of time decay. You lose at each step a bit of time decay, and in this way you compensate the strip, the complex value of omega c. Obviously, I can do this only a finite number of times, and after that, I need to stop, and I stop here. Thank you.
Thank you very much. Yeah, questions?
Just to summarize the last few steps, it's like lambda is like the case in which you would have a periodic modulation but with an imaginary frequency.
No. Is that omega, which is obviously the derivative of the integral part of h of I, is a general function. So when you complexify, omega is complex. It's no longer real, purely real. It's complex. Then this gives you a complex contribution, the exponential. So it becomes real.
Yeah, but what I'm trying to say is that if I have, let's say, let us assume the Hamiltonian has something like e to the minus lambda t, the beginning, let's say, times a function.
Yeah.
Then I could view the time, or lambda t, or the time itself, as an angle, but with a frequency in front that is imaginary.
Yes.
So it's equivalent to that, let's say, more or less.
Yes, in some sense, yes, because if you have if you have an oscillation, you can recover the term in the formula, and then you have.
So, more questions? Okay. No? Let's take this speaker again.
Thanks.